Hello everyone, welcome to this video. My name is Amir Senahari. I'm a Google Earth Engine expert. Today I'm gonna show you how to download digital elevation model for your study area through the Google Earth Engine platform. And I want to show you what kind of digital elevation models are available in different spatial resolution in the Earth Engine data catalog. Let's go to the Earth Engine code editor. In the first step, you need to identify your study of area or region of the interest. It doesn't matter where is your desired area, where is your region of the interest. This tutorial can be used for all around the world. And now I'm gonna select a part of my own country, Iran. I go to my country, a part of that, for example, in the north of Iran, we have the mountainous region here, and also it's a very helpful place to show the elevation variations. And also you can use or download digital elevation models for the smooth and rough region, and no matter what kind of region you are working, because when we are working with digital elevation model, we need to get elevation values for each pixel. And now for the first step, I'm using rectangle tools or drawing tools available here, and select a region of the interest in my own country. And then through map.center object, make a focus on the study area that is geometry already named here. So then we need a variable. The first one is SRTM digital elevation model. SRTM equals to, through the search places and dataset, you can search through the data catalog to find the SRTM digital elevation model that is available. SRTM, ALOS, and ASTER are the most popular digital elevation models that people use in their projects, and with 30-meter spatial resolution available, and you can use it for all around the world. Or if you want to know more about the digital elevation models, through the Browse Data Catalog, go to the catalog part and data tags, and then browse your desired data based on the tags. It's very valuable assets in Earth Engine, enabling you to find your desired product through the tag. For example, if you write digital elevation model, you can see that 36 dataset uploaded in the DEM tag or under the tag entitled DEM in the Google Earth Engine platform. So here a diverse set of digital elevation models with diverse spatial resolution are available. Some of them are local and some of them are global. For example, this is for Australia, this is for the Netherlands. But SRTM products mostly available for the all around the world in different versions. For example, here we have SRTM digital elevation model version number 4 that is collected elevation values by the radar data in 2000s, and you can see that its elevation available for all around the world with 90-meter spatial resolution. When you are working on a national scale or a little bigger scale, 90-meter spatial resolution is good enough. But if you want to have more detail about the region of the interest in local studies, would be better to use digital elevation models with 30-meter spatial resolution. So if you browse more into this page, you can find, for example, ALOS DSM Global with 30-meter spatial resolution. This is another radar-based digital elevation models that is collected since 2006 to 2011. It's available with 30-meter spatial resolution. Digital surface models, usually including the man-made and the natural phenomena elevation values on the Earth's surface. And one of the main advantage of ALOS DSM is that it is its coverage is global, but SRTM only available for the mid-latitude regions. For the higher latitude regions, for example, above 60 degree, you can't have access to the SRTM. For example, if you are working in a Scandinavian country, and also most of the time you will have gaps regarding to the elevation values unless you shift elevation data from SRTM to the ALOS, and these are very helpful products. And for the high latitude regions, I usually use ALOS as a good alternative in this regard. So, and if you browse further here, the other kind of digital elevation models are available based on different standards, specifically for the hydrological studies. And here you can see that the NASA digital elevation model with 30-meter spatial resolution is available. This is same as the SRTM values. Actually, this is the SRTM value. SRTM digital elevation model with 30-meter spatial resolution that is very popular among remote sensing users to get for the mid-latitude regions. As I mentioned earlier, the only negative point, or the main negative point about the SRTM elevation model, is lack of data for the high latitude regions. So, but as most of the users working on mid latitude regions, still you can use this in the most of the projects. So, for example, I want to use NASA digital elevation model with 30-meter, and to know more, you can refer to the descriptions and also the citations available here. It's very important to cite to the data you are using in your papers and projects. So back to programming, and now I want to use NASA digital elevation model, NASA DEM here, and then you can see that with 30-meter spatial resolution, both are available. I think both of these products are same. I didn't find a very clear difference between these two kind of products, and also most of the time they have a very close results. NASA digital elevation product imported into the code with it including 3 bands. It is an image and no need to define any filter here. Just we need to assign the image to the SRTM, but the only thing matter is select the appropriate band. There are different bands available here. As we are working on elevation values, we need to select elevation band. Its unit is meter. So, and now through the .select function, we can select elevation band here, and then through the map.add layer, you can show or visualize the digital elevation model that is called into your code. Just clip it based on your study area or the geometry, and then I leave the visualization characteristic empty, and also the name in the layer setting is DEM 30-meter, and then to avoid from automatic visualization, I set the false here. So save your code and run it again to see the elevation changes for your study area. So you can see that we have a new layer here. It is very fast and quickly showed here, and also then you can increase the contrast that's showing elevation ranges in this area from 300 to above 2,800 meter from mean sea level actually. So here we have a grayscale images, the brighter colors showing higher elevation, the darker regions showing lower elevation. By the inspector, if you click on each pixel, in the right side you can see the elevation value that is selected, the elevation value for each pixel. For example, the selected pixel has 350 meter elevation above or from the mean sea level, or this region, for example, if I scroll down a little, for example, this region of higher elevation, it is more than 2000 meter, and also this area as a downstream, you can see that its elevation is around 300 meter. So, and then in the next part, if you want to have a general look or have a very quick look about the range of elevation changes in this area, you can use the histogram function here. through the print, we can make a histogram chart for the layer we called earthengine.chart.image.histogram. The input image is SRTM, and then SRTM and the location of the interest is the geometry, and then spatial resolution could be 30. But if you face any errors regarding to the spatial resolution because of the high density of pixels in this study area, you can increase the number of the value of spatial resolution to avoid some type of errors. So then run your code. As you can see that I have the same error here because of the large number of the pixels in this spatial resolution. There are some restrictions and limitations in Earth Engine platform, and also in order to have a light code and also run it quickly and fastly, for example, I reduce the spatial resolution to 100 meter, and now you can see the elevation changes in this region. If you click on this icon, you can see the elevation ranges by histogram from minus 32 meter below the Earth's below the mean sea level to above 3,000 meter above mean sea level. Elevation values changes, and also this is the multimodal histogram that's showing that the elevation, this is the rough places, and elevation varies from downstream to the upstream, and also with multi-peaks, it showing that certainly we have mountains and also some flat regions, and on it goes. Lots of information you can get from the histograms that you make for digital elevation models, and also there are good signs when we have multimodal histogram in digital elevation model, for example, showing we are working on rough places and also with lots of ups and downs in the study area. So for the next step, I want to show you how we can get some complementary product when we are working with digital elevation models, something like, for example, slope of a study area or aspect of the study area. So it's very simple. Just make a new variable as slope, get digital elevation model, or we can write it like this: earthengine.train. earthengine.train. You can see that through the train, a diverse set of functions are available regarding to the train analysis. For example, if you want to get an slope, just click on the slope, and then input image could be SRTM, and then through the map.add layer, you can show or visualize the SRTM that is clipped based on the geometry of interest or region of interest, and then its name is slope. And then the next part we have, after slope, you should input false here or set it false to avoid from automatic visualization. Run the code again, and a slope is available. Just have a zoom in and increase the contrast. The slope is based on degree here, and the higher slope showing brighter and lower slope or surface regions showing with the dark color. And actually you can use histogram again to show to see the range of slope that is changing in your study area. And if you need more information regarding to the slope function, just go to the docs and train and write the train in the search, and you can see that all the algorithm and functions working with train data available here, and just click on it and read the descriptions, and also helps you to know that, for example, the slope is in degree or, for example, radian. But here we can assure that This is based on the degree value. For example, if by inspector you select a region or pixel here, this is 102 degree, or this part the slope value is 20 degree and ranges from 0 to 90. So, and also you can do this process for aspects. New variable, another new variable, but this time aspect equals to Earth engine dot terrain, Earth engine dot terrain dot aspects, and by the aspect we want to get aspect of elevation or slope in this region, and then show it by map.addLayer, but this time we need to aspect that clip based on the region of the interest, and then we have aspect and false. Run the code again, and now aspect is available, showing the direction of the slope, the direction of the region or direction of the topography in this region by the values. And if you go to the description function description here, you can see that, for example, regarding to the aspect there is a description, and aspect will be in degree. And also if you search on the Google, there are a lot of tutorials that showing you which number showing, for example, which direction, and based on you can interpret the results. So, and also another important function helping you here is Earth Engine Train.products, that enabling you to have a slope, aspect, and simple hill shade from a train model. You can calculate all of them together by a same function. For example, here I want to make a new variable. This is, for example, product equals to Earth Engine dot train, Earth Engine dot train dot products. The only input is RTM, and then through the print you can see that the result and check it on. If you go to the console, 4 bands available here, and you can see that the elevation value as the input, slope, aspect, and hill shade, all of them calculated, and you can get and also you can export all of them together from the Earth Engine to use it in the ArcGIS Pro or any other softwares for the further processing in your modeling and your research work. And to do this, just we need to use export function here. Through the export that image to drive, you can define different arguments and save the final results. The input, one of the important argument is the image equals to product, and as the product is an image, we don't need to use that advanced or something like that for the study area, and would be better to keep your study area based on the geometry or shape file you are using for this study. And the next is the name of the output file that is defined by the description. For example, I want to save it as a DEM product or elevation product. You can choose any other kind of names you need, and the scale, if you want to get the output with 30 meter spatial resolution, put it 30, or if you want to have less spatial resolution, 100 is enough. It depends on you, but with the original pixel size is 30 meter, and the region of the interest is geometry. And one more thing I missed is that when you have a layer stack with different value ranges, such as elevation, slope, they have different kind and different range of values, and in order to save all of them in a same stack, you need to set that float to avoid from some errors that happening when you want to download multiple products with different range of values. So, and instead of the region, and also in addition to the region, we need to set CRS, the spatial resolution. To get the original spatial resolution, just write the product here, product.getinfo.crs. We can extract the original what is that? The original coordinate system of input images to set it for the output. And the next is the folder that you want to save it in your Google Drive. For example, I want to make a folder in the Google Drive as digital elevation model to save the result. This result is specifically separated from the other files that is available there. And I think all the important criteria defined here, and you can save your code and run it again. So go to the task. And also one more thing, when you are working with the fine spatial resolution data, for example 30 meter, it's important to set maximum pixels for the output. The maximum pixels for each output, the maximum value is 1E13, and it's helping you to get the maximum pixels for each product, and to avoid from cutting your image into different pieces. It's helpful. So then run it and wait until the saving process is done, and turn to the blue color like this. And also it's very simple to work with the digital elevation models because everything is ready and all of them are available as image format, and you don't need to convert them to the for example multi-temporal combinations, and with the less programming techniques, and also most of the important techniques is available here. And another advantage of getting a digital elevation model from the Earth Engine is that you don't need to do mosaicing process. For example, when you want to download a DEM from Alaska website or from the Earth Explorer website, you have to download multiple frames to cover your study area and do mosaicing process or something like that. You need to do further processing to get the final and desired digital elevation model for your study area. But in Earth Engine, everything is ready and no need to do any mosaicing. Just I want to show you one more example about the ALOS data, because the ALOS DSM values are available in image collection format through the search places in dataset, type ALOS DSM global with 30 meter and then import it into the code. But the main difference between the ALOS DSM and the other digital elevation models available in Earth Engine platform is that the others are available in image format, but the ALOS is the image collection from 2006 to 2011. But you can turn it from image collection to the image by getting a mean function or median function. It's very easy. The only difference between these two kind of product is converting image collection to an image, because elevation value doesn't change a lot in 30 meter spatial resolution. And also we don't need to do sometimes there is analysis for the most of the time. As you seen here, we use the digital elevation model that is created in 2000. Why? But we are in 2004 because the elevation value doesn't change a lot in such scales. So, and for example here, make a new variable for the ALOS and assign the image collection to the ALOS, and then select the desired band. If you go to the description here into the bands, the digital surface model is available, and height above the sea level, and then through the dot select the bands. And to convert it from an image collection to an image, you can use .mean. It's very simple, and also the rest of processing is same as what we have done for the SRTM. For example, I want to get a histogram of ALOS for this region. For example, it's very easy. Use print user interface dot charts. Just I want to show you some differences between products for elevations, because these products DSM and DEM have some differences in the absolute values. So that histogram instead of the image for ALOS is the image here, geometry region of the interest, and the scale is 30 meter. But as you've seen in this tutorial, we have faced with the high density of pixels problem, and then I reduce the spatial resolution to 100 meter here, and you can see that chart is generating, and also the range of values is really close to each other, and no clear differences watched, for example, or detected in the pattern or even in the minimum and maximum values. They are almost same and no clear difference. But the main advantage of the ALOS DSM is that if you are working on high latitude regions such as Russia, Canada, and Finland or Norway, for high latitude regions, it is also available, but we have lack of SRTM DEM for high latitude regions. So in the task, you can see that it is still in process because it has fine spatial resolution. Maybe it takes a little more time to be stored into the Google Drive. I hope this tutorial could help you to deal with the digital elevation or elevation values for your study area. If you faced with any problems or any challenge in this tutorial, you can reach me out in my YouTube page and put your comments. I will try to help you to solve your issue in these regards. Thank you for watching us.